All right. So this is the first final review session for MAP 2302 differential equations, summer C. Um, so what I want to do first is I kind of want to explain how the final is going to go. I said this out in an announcement, but just in case you didn't hear that yet, I want to kind of explain that. So the final exam is going to be this Friday, and just like all the other tests, you have from 9 a.m. to 9 p.m. to start the exam if you want to get the full amount of time. This time it's going to be 2.5 hours, so it's going to be a little bit longer than usual, but it will have 2 more questions. It'll have 22 questions, unlike before. So it'll be a little bit longer, but proportionally, I still think you have a fair amount of time. And I don't think many people should have problems finishing. The exam will be over everything we've done this semester, so lessons 1 through 28, but with the following caveats. So first of all, there's no lesson 10 in there. That's first order applications. We didn't have a test on that earlier. We're not going to have a test on it now. Same thing with Euler's method. I forgot which lesson specifically that was in, but that won't be on here because that's better done using a computer program, and it's harder to do that on the exam. So no Euler's method. There's also not going to be anything involving like weird trig identities, like sum to product law or product to sum laws. Don't worry about those. The one set of trig identities I would know would be like the half angle identities, like sine squared is 1/2, 1 minus cosine of 2 theta, etc. I would definitely know those, but yeah, you don't need to really know any other ones. Oh, I guess I would know that sine squared plus cosine squared is 1, but hopefully you guys know that one by now. And then also there won't be any integrals that require trig sub on the exam. So don't worry if you're like, oh God, I forgot how to do trig sub. That's totally okay. We're not going to have anything like that on the final exam. So don't spend time studying for that if you've been doing that. There may be integrals like 1/1 plus x squared or things that kind of look like that. Remember, those turn into arctangents, so you don't need to do trig sub for that. So that's possible, but that doesn't really need trig sub. Also, one final note about the exam. So actually 2 final notes, I guess. Series will be on there, but since it wasn't on any of the older exams, it'll be a bit more heavily represented. I think there might have been some confusion about that. It only takes up 1/7 of the class, but it's going to definitely be more than 1/7 of the exam. I'd say maybe like 4 to 6 questions-ish, maybe around there, maybe like a quarter about of the exam will be on series of things we've done in the last module. But then the rest of it will be relatively evenly distributed among all the other lessons. And then finally, you'll be provided both with that same Laplace transform table that you had last time, as well as a series of a table of common Maclaurin series that will also be given to you in the same way in a link that you can open up in a separate window and use during the exam. So you'll be provided with those. So no need to go crazy memorizing anything like that. Let's see. I think that's all the details about the exam. I just want to emphasize again. I'm going to remind you like 1 or 2 more times, but I want to take another opportunity to remind you. Don't forget that this Friday at midnight is like the hard deadline for submitting everything. So if you homeworks or lecture quizzes you haven't done yet, make sure you get those done by this Friday at midnight, because at that point it's not going to accept them anymore. So please be sure to finish those if you haven't already. Let's see. I think that's all the bookkeeping kind of announcements. Now, one topic I want to go over that I think might be helpful is about taking the derivative of a power series. So I think it was one of the homework problems. I don't remember which homework it was on, but you had to take the derivative of the series for sine, and you wanted to see what you would get. Now, we all know the derivative of sine is cosine, so hopefully we'll end up getting the series for that. But I think there was a little bit of confusion about that. So let's start off with sine of x. If we look on our Maclaurin series chart, it's going to be the sum from 0 to infinity of -1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. Let me know if you can't really see what I'm doing. I'll try to make it better. So anyways, this is sine, and we want to take the derivative of this and see what we get. So obviously the derivative of sine is cosine. Now, when we take the derivative of a series, the nice thing about series is that all we have to do is just use the power rule on x to the whatever power. That's all we have to do. So we can just keep the same sum. We can keep this -1 to the n. We can keep this 2n plus 1 factorial. The only thing that's going to be different is this x to the 2n plus 1. So we multiply down by 2n plus 1 and lower the power by 1, which will give us x to the 2n. Now, this doesn't entirely look like the cosine series. That is a 2n factorial on the bottom. But what's going to happen is that 2n plus 1 will cancel with the 2n plus 1 inside this factorial. And then, OK, what will the factorial start with then? It'll start with 2n. So if we cancel this and, I guess, this out, we end up having 2n factorial. So let me kind of summarize that. So now we have -1 to the n, x to the 2n over 2n factorial. And there we go. And that's the normal series we expect for cosine. OK, well, what was weird about this? Well, so in a lot of your Calc 2 classes, you may have heard that when we take the derivative of a series, you need to increase the starting index by 1. So for example, we started with 0 here. You may have learned that you're supposed to turn that into n equals 1. And unfortunately, you may have been misinformed because that's not entirely true. When you take the derivative of a series, by default, the index stays the same. The only thing I changed about the series was this x to whatever power. That's the only thing that changes. You might be like, well, Dr. Manley, I've definitely seen it happen before. You've probably seen it happen in this particular case. So a lot of times we have y as a Taylor series, 0 to infinity, an x to the n. And if we want to take the derivative of that, and we just do the power rule. So we have n x to the n minus 1. Now, what a lot of people like to do here is they see like, oh, wait a minute. If I start at 0 and I put 0 in there, what will I get? I'll just get 0. So I might as well just not even include that term and just change this to start at 1. That's the only time you can change your index freely like that, is when the index you're getting rid of or adding in makes the term in there be 0. In the sine example we have, if we plugged in 0 in there, we wouldn't get 0, we would get 1. So we weren't allowed to do it then. So the only time you can change the index is when the resulting term will end up being 0 if you plug in the starting number. So I just wanted to clarify that. By default, the index doesn't change, but some people like to change it so they're not including like an extra 0 in there. That's why it seems like you change the index when you differentiate, but that's not always the case. All right, I just wanted to clear that bit up. A lot of people were asking about like an alternative way to do stuff in lecture 28, because it takes a long time to do that stuff. So I posted another video about that a little bit earlier today. So I recommend going and check that out. But of course, I'm happy to do more problems like that now if you want. All right, well, that about does it for me talking, at least for now. So you guys have any questions, anything you want to talk about or ask? I'd be happy to help you out.
Yeah, I have a question about homework, the last homework, where you have to find the power series expansion, where you're multiplying like by a cosine of x or by like a e to the x.
Yeah, okay, let's take a look at that.
Like specifically question 7 in the last homework.
Question 7. Okay, yeah, let's take a look at that one. Actually, I do this one in my video, but we can go over it here too. So this is a tough differential equation because it has not even a polynomial, but an actual like complicated function like cosine in there. We have 4 cosine of x times y prime. And note that the y prime is outside the cosine. And then we have minus 4y is 0. And then we have some initial conditions. Y of pi over 2 is 4. And y prime of pi over 2, well, that's going to equal 5. And what we're tasked to do for this problem is to find the first 4 non-zero terms in the power series expansion. Like I said in the other video, when we do when they're asking you for the first however many terms, one way to do it is to just figure out what the coefficients will be manually rather than using series to get a recurrence relation. Well, how do we do
Did you say, sorry, did you say that you worked this out in a video already?
Yeah, I did. Do you just want to ask another question instead, or?
Well, if you already worked it out, I don't want to waste your time then.
Okay,
Where can
I
I find that
understand.
video?
All right, yeah, if you want to go see this one, check out my other video.
Where can I find that?
It should be on the YouTube channel. I posted a link to it in an announcement that I sent out earlier today.
There's a YouTube channel?
Yeah, it's where I post all of my
Oh, okay.
my recordings and stuff. Yeah, you should be able to see it on the announcements of Canvas.
Oh, okay. Okay. I'll try and find that.
Let's see. So Hugh has a question. He wants to go over number 7 on the practice final. Yeah, there's the link to it. Let me pull that up real quick. Okay. Practice final. Let's see. Okay. And then number 7. Okay, so this one, it's kind of going over some old material. This one's talking about using variation of parameters to solve a problem. So let's take a look at what we have here. We have t y double prime plus 6t minus 1 y prime minus 6y. And what's that equal to? That's equal to 2t squared e to the negative 6t. Okay, so we need to solve this equation. We want to find both a homogeneous and a particular solution for this. Now, they were nice enough to tell us what the homogeneous solution is. They say that our first part of that will be 6t minus 1, and our second part of that will end up being e to the negative 6t. So they were kind enough to give us our 2 homogeneous solutions. Now, what we could do is we can use those to generate the particular solution. And that process is called variation of parameters. Now, the first thing we need to do before we get to that is we need to find what's called the Wronskian involving these solutions right here. So the Wronskian is what's called the determinant of the matrix, where we put in our first solution and then its derivative down here, and then the other solution and its derivative down here. And then we sort of, it's kind of like cross multiplying. We just multiply these two and subtract those two. So what do we get? We get 6t minus 1 times negative 6 e to the negative 6t. And then we subtract, and we get 6 e to the negative 6t by multiplying those two together. And oftentimes this will end up simplifying, and this actually ends up being one of those times. So we see here we have negative 1 times negative 6 e to negative 6t. That will turn into positive 6 e to negative 6t. But then that will cancel out with this bit right here. So this part and then the result from multiplying by that 1 go away. So what's our Wronskian? It's going to be negative 36t e to the negative 6t. So that's going to be our Wronskian. Now, what do we do with that? Well, it turns out that there's a formula involving both the Wronskian and what appears over here, as well as our solutions right there. But I actually forgot to do one thing. Before we can use this formula, I need to make sure that y double prime is by itself. Variation parameters won't work quite right if it's not on its own. So I'm going to divide everything in this equation by t. So dividing this by t makes that go away. I have a divided by t right there, divided by t right there. And the most important part is dividing this right-hand side by t. 2t squared divided by t will just give me 2t. Okay, so now that I have that taken care of, let's see what our yp is going to end up being, or our particular solution. Okay, let me write up our Wronskian so we don't forget it. Negative 36t. All right. So for using variation parameters, we need to end up doing 2 integrals. The first integral we need to do is negative y1 times the integral of y2 f of t divided by our Wronskian dt, where f of t is this right-hand side after we've divided out by what's in front of y double prime. All right, so filling in the blanks for our particular example, we have negative 16 minus 1 in there, and then we have an integral, and then we have y2, e to the negative 6t. And then we have our f of t, so that's 2t, e to the negative 6t. And then we divide by our Wronskian, which is negative 36t e to the negative 6t. Now, typically, there will end up being a lot of cancellation for these integrals, which is really nice because this integral looks really ugly right now. So what's going to happen is these e to the negative 6t's will cancel out. These t's will cancel out. This negative 2 over 36 can come out to the front as 1/18. And then this negative will cancel with that negative. And I think that's about all we can do to simplify this. All right, so let's see what happens then. So we have 6t minus 1 divided by 18. And then now we just have the integral. The only thing that's left is this e to the negative 6t. Okay, and then thankfully, that's a pretty easy integral to do. We just keep it the same, but then we divide by the coefficient of t. So we're going to divide by a negative 6 here. So we end up getting 6t minus 1. Let's see, 6 times 18. So we have negative 108. We have e to the negative 16. Yeah, a lot of the problems in these practice things or homework, they can be a little bit icky, unfortunately. But anyways, so this isn't our entire yp, though. This is only the first half of yp. In order to get the other half of yp, we need to do a similar integral. We need to end up doing y2 times the integral of y1 f of t divided by the Wronskian. That will give us the second half of yp, and then we'll be finished up. All right, so let's see what this integral ends up being. Hopefully it's something nice. I'm gonna copy this up here so we don't forget. So we have 6t minus 1 e to the negative 6t, negative 108. All right. Okay, so let's plug in everything we have. Y2, that's e to the negative 6t. And then y1 is 6t minus 1. We have f of t, which was 2t e to the negative 6t. And then our bottom, which is negative 36t e to the negative 6t. All right. So let's see what's going on with this one. So once again, we have a lot of nice cancellation. These exponentials go away. These t's go away. This once again turns into negative 1 over 18, which we can move out. So we have negative e to the negative 6t over 18 times the integral. And then the only thing left in there is that y1, 6t minus 1. And then thankfully at this point, we're back to doing polynomials here. Those are never too hard to integrate. So when we integrate this, we have negative e to the negative 6t divided by 18. And if I integrate this, I raise this to the second power and divide. So I have 3t squared. And then this will be minus t right there. Okay, so there is our yp, the second half of yp. So all in all, our solution will end up being the two homogeneous pieces. So our y will end up being c1, 6t minus 1, plus c2, e to the negative 6t. And then we throw in our particular solution. So that'll be minus 6t minus 1, e to the negative 6t over 108. And then minus e to the negative 6t over 18 times 3t squared minus t. So there we go. So there's a perfectly valid solution for this differential equation. Now, if you did that on a written exam, hey, that's wonderful. You're totally done, and that's totally right. But if you look at these multiple choice answers for this question 7 on the practice exam, you may not see anything that actually looks like that. So let's see if maybe you could do some algebra or something else to get it to look like one of these answers. Now, first off, I think there's actually going to be some cancellation with this. So notice, oh, we already wrote that down. So notice here we have negative 6t e to the negative 6t over 108. And 6 over 108, that simplifies to be 1 over 18. So we have a negative version of that here, but then we have negative, negative, so a positive version of that right here. So if we were to FOIL this out and do the algebra, actually, I won't skip steps, I'll FOIL this out. So this part right here, our yp, so I'm going to just ignore the homogeneous solution now. We know that that's definitely going to be there. So our yp will be negative t over 18, e to the negative 6t, plus e to the negative 6t over 108, minus t squared e to the negative 6t over 6, and then plus t e to the negative 6t over 18. That's what I get if I FOIL all of that stuff out. And now it's a little bit easier to see that this and that can cancel. Okay, that's good. Now, if we look at this term right here, we have a constant times e to the negative 6t. Now, this is something that comes up a lot with variation parameters. What do we do with this? Well, we already have in the homogeneous solution a constant times e to the negative 6t. So what happens is that this piece just gets incorporated into that constant in the homogeneous solution. So we could pretty much just ignore that. So the only thing left in our particular solution that we really care about is this negative t squared e to the negative 6t over 6. That's going to be the only piece left in our yp. And thankfully, that actually does end up matching with one of the answers. So doing this is kind of tricky enough, but then eventually you have to make sure you simplify everything, you cancel out, and then you eliminate terms that are repeated because of your homogeneous solution. So we end up getting, let me just write down our final solution here just for completeness. So all in all, we get y is this stuff, and then minus t squared over 6 e to the negative 16. All right, so that's variation of parameters. It does unfortunately take a while, but it's good for equations we really wouldn't have another way of solving. All right, let's see. So JT asks if we can do lesson 23, question 10. All right, well, let's take a look at that. Let's see. All right. Let's see, lesson 23. Open that up. Question 10. Okay, so this one is all about solving integral equations. And that's something we talked about back in the Laplace Transforms section. Let's take a look at this one. All right, so our integral question this time is going to be y prime plus 27 times the integral from 0 to t of t minus v times y of v dv, and then all that's equal to 17. They also give us this initial condition that y of 0 is going to be 0. Okay, so with this information, we're going to try to figure out what y is. And by the way, this is a technical term. This is technically an integral differential equation because it has both an integral and a derivative in it. But it's solved the same way no matter what. We're going to use Laplace transforms to deal with this. So as with every Laplace transform problem, the first thing we do is we just take the Laplace transform of both sides. So the Laplace transform of y prime will be s times Laplace of y, which I'm going to write as a capital Y. And then normally we do minus y of 0. But in this case, y of 0 is 0. So we're just going to ignore that. Then we have 27. Laplace doesn't care about constants. Now, if I take the Laplace transform of this integral might look kind of familiar. This is actually the convolution integral. And remember, those work really nicely with Laplace transforms. All it is going to be the Laplace transform of this function, which is really like a t, and then times the Laplace transform of this function. So the Laplace transform of t, if we look on the chart, would be 1 over s squared. So we're going to have an s squared down here. And then Laplace of y, that's going to be this capital Y right there. So since this guy was the convolution of t with y, when we do the Laplace transform, we just do Laplace of t times Laplace of y. And it ends up getting us this right here. And then finally, on the other side, we have another t, so that'll be 7 over s squared, like that. Okay, so we finished the Laplace transform part. Now the next step is always to solve for capital Y. Unfortunately, these integral equations, they always end up getting these nasty fractions. So I'm just going to kill the denominator here. I'm just going to multiply everything by s squared. So I have s cubed times y plus 27y is equal to 7. Okay, so hopefully that makes things a little bit better. And then I'm going to divide, so I can factor out a y here, and I'll get s cubed plus 27 times y. So I can factor a y out of that. And then I'm going to divide to the other side. Don't need that anymore. So y is going to be 7 divided by s cubed plus 27. Okay, so now at this point, now we need to figure out the inverse transform of 7 over s cubed plus 27. Now, this might seem kind of strange. Like, okay, this looks kind of hard to factor. But what we have here, if you look carefully, is we actually have a sum of cubes. And there's a particular way that a sum of cubes will always factor. And that's going to be 7. And then the first part, we always have whatever's being cubed just added together. So we have s was cubed, and then 3 cubed is 27. We just have that piece there. And then we have, for our second piece, s squared minus 3s plus 9. So we kind of alternate signs until we get to the end with a positive, and we have a negative right there. So this is a kind of a special way of factoring the sums of cubes. Now, if you didn't know that, that's totally fine. I guarantee you're not going to have to factor sum of cubes in the exam. But this is how we're going to do that. And then now that we've factored this, then what we're going to do is we're going to do partial fractions. We're going to do partial fractions so we can split these guys up. Unfortunately, we would normally try to factor this one, but that one's not going to factor nicely. All right, so what I'm going to do, I'm going to do the partial fractions, and then I'll kind of just explain verbally where to go from there. And unfortunately, this guy in particular, completing the square with that, which is what we're going to have to do, is going to be really annoying because we're going to start getting a bunch of fractions everywhere. So that's not going to be great. That's probably why all these answers look so complicated. But I'll at least explain what we're going to do so we don't spend the whole review just doing a bunch of work. Oh, you say you got it from here. Okay, yeah. So let me just summarize the steps. So we do partial fractions, and then complete the square. And then we're going to have e to the something from the s plus 3 term. And then we're going to have sine and cosine coming from the completing the square part of this. And so that's how we would finish this off. So the main part was just dividing by this. Oh, we also have a comment to use synthetic division to factor it. Yeah, that's absolutely true. I totally forgot about that. Yeah, you can also just, since you know that -3 would be a 0 to that, you can divide -3 into there, and you would get this as a result. That's a good point. That's another way of doing it. All right, so there we go. So that's that question. We got that integral equation all set up. Anyone have any other questions? Any other stuff you guys would like to go over? Happy to do anything from lesson 1 all the way up till now. Could you review Cauchy-Euler equations and reduction of order? Yeah, so I'll go over those real quick, please. Oh, everyone sent stuff at the same time. All right, good. We got a few questions after that, too. Okay, so Cauchy-Euler equations, those ones are where we have a differential equation that looks like this. We have ax squared y double prime, or you'll see t's a lot as well, plus bxy prime plus cy is equal to 0. Although sometimes we can have a right-hand side for that as well. And this is what's called a Cauchy-Euler equation. Now, these equations actually have a particular looking solution. It's usually just x to a power. And how do we get what power that is? Well, what we do is we solve a polynomial equation, kind of like we did back in, I think it was module 3 of second order equations. But it's going to look a little bit different from the polynomial back then. The polynomial this time that we need to solve is ar squared plus b minus a r plus c is equal to 0. So we end up solving that equation, and whatever the roots are for this, let's say we have like r1 and r2, then our solution is going to be y is c1x the r1 plus c2x to the r2. Okay, now there are a couple caveats to this. What happens if we get a repeated root? Because we know back from module 3 that something weird happens if we get a repeated root. In that case, if we just get 2 copies, let's say of r1, so let's say we just get r1 and r1, then our solution will be c1x to the r1, and then we'll have c2 ln of x times x to the r1. Let me get that a little bit better. X to the r1, c2 ln of x times x to the r1. And if for some reason you were solving maybe a third order equation and you got like a triple repeated root, the way this pattern goes is instead of adding powers of x, like we did back in module 3, we're instead adding powers of ln of x. So we had a triple root, we would have these two, and then c3 ln of x quantity squared times x to the r1. So we use ln of x as sort of bumping things up when we have a repeated root. And then finally, so as we know, quadratic equations can sometimes have complex roots, so roots that have imaginary numbers in them. So what do we do when we get one of those out of this equation? Well, let's say we get that our roots are a plus or minus bi. And remember, the imaginary roots always come in conjugate pairs. So it'll always be a single number a and then plus or minus the same number times I. So what do we do when we get that situation? Well, first of all, we're going to have y is c1, and then we still have x to the a. But this time we're going to have sine of b ln of x. So this b is going to go inside our sine function times this natural log. And then we have c2 x to the a, and then you guessed it, it's going to be cosine of b ln of x. That's what our solutions look like when we have imaginary roots for Cauchy-Euler. And just like, also just like in module 3 with the original linear equations, if you have something on the right side, you can do variation of parameters, or sometimes even undetermined coefficients to get what the particular solution will be. So that part's exactly the same as before. And then reduction of order. So reduction of order is where we know one solution to an equation, and we want to generate another solution to an equation. Like maybe we want to use variation of parameters, but we only know one of the solutions. So how do we get the other one? Those ones are kind of hard to make up on the spot. Let me see. Was there end up being one in the practice exam? Let's do that. Oh, whoops, I was looking through the. Okay, let me go back to the section that was in. That was in, sorry, that was in, pretty sure that was in lesson 17. Take a look at that. So exam 2, number 15 is Kosher Euler. Yeah, so that was Kosher Euler. So yeah, we finished talking about that, but I was looking for reduction of order, which is a bit different. Okay, I found an example here in the homework. So I'm just going to set this one up. It's a little bit tedious, but I'll just show you how we do this. We have 2x plus 5 y double prime minus 4 times x plus 3 y prime plus 4y is equal to 0. And they say that x is greater than negative 5 halves. The reason why they say that is they don't want this to be 0. And they tell us that one solution to this equation is e to the 2x. And what we could do is we could use what's called reduction of order to get the other linearly independent solution to this. So the first thing we need to do, just like all of the things that involve reduction of order or variation of parameters, we need to divide by whatever is in front of y double prime. So when we do that, we have y double prime minus 4, and then we have x plus 3 over 2x plus 5, y prime, and then we have 4 over 2x plus 5y, and then we still have 0 over there. So first we need to get the equation like that. And it's important this time that we do that because we're going to be paying attention to what this term is. I think they call it p in the notes. It's the thing that's in front of y prime. That's going to be very important for us. Now, the way we get our second solution is we use the following formula. So y2 is going to be y1 times a particular integral. It's going to be the integral of e to the negative integral of p dx, and then we divide by whatever y1 is squared, and then we're just going to integrate that. So really, we have two integrals to do. We have to integrate first this part right here, this p, and then we have to divide by y1 squared and then integrate that. Now, thankfully, if these problems are set up right, that's why I didn't want to make one up, because oftentimes these integrals are really hard. A lot of stuff will just cancel in here, and then it'll end up being an easy integral. Now, what's going to happen this time is this guy right here, if we were to integrate this, we would end up getting some kind of natural log. And this e to a natural log would cancel out, and then hopefully we would get stuff down there canceling out as well. So that's kind of how these things go. You usually get a log that cancels with the e right here, and then that's stuff that we get from canceling will cancel with the bottom, at least for the most part. And then the integral is hopefully doable at that point. So it just kind of boils down to doing this integral right here, and then we end up getting our second solution. So that's sort of reduction of order in a nutshell. It just kind of revolves around this formula right there. Let's see. All right, so is that okay, Andrew, or do you want me to like go through this a little bit more? Like, do you want me to actually like finish the problem? Okay, that was good. Okay. All right. Let's see. So Naomi wants to do lecture 26, number 2. Okay, let's go to that one. Let's see. 26. All right. Number 2. Okay, so this one is all about multiplying power series together. And unfortunately, it's not as easy as just taking the two formulas for the series and just multiplying together. It'd be nice if they were that easy, but it's a little bit trickier than that. So let's see how we would do it. So in this problem, they want us to get the first 3 non-zero terms of f of x times g of x as a series. And in this one, they say that f of x is going to be e to the negative x. And then we have g being 1 over 1 plus x. So the first thing we need to do is we need to come up with a series for each of these guys. So we need to come up with a series for this and a series for that, and then we can FOIL them together. And we need to FOIL them together because essentially series are just really big polynomials. And kind of like how we have to FOIL polynomials, we have to FOIL series as well. All right, so let's take a look at this one, e to the negative x. Well, that actually looks very similar to a series that we've seen before. It looks very similar to just e to the x. So e to the x, that series, is the sum from 0 to infinity of x to the n over n factorial. So that one, hopefully you've seen that one before. That's a pretty common series. Now, we're very close to what we want. It's just that this is e to the negative x. So all we need to do to get that series is just change this x to be a negative x, and then change this x to be a negative x. Now, since this negative is raised to the nth power, that means we're going to have the sum of negative 1 to the n, x to the n, over n factorial. All right, so this is going to be our series for e to the negative x. And then we're actually going to do something very similar for this 1 over 1 plus x. You might remember, or you could just look on the table for the homework, that 1 over 1 minus x, the series for that is about as simple as you can get. It's just x to the n. Now, just like before, we're not interested in this series. We want 1 over 1 plus x. So what are we going to do then? Well, if we do the same trick, we stick a negative x in here, that will turn into a plus, and then we'll have our series. So we have 1 minus negative x, or 1 plus x, is this series right here. And just like in the other one, we want to write this as the sum from 0 to infinity of negative 1 to the n, x to the n. You always want to try to get the x on its own. That's one thing you always want to do with series. Try to get the x on its own. Or x plus or minus something. That's okay, but like nothing multiplied by the x. All right, so we have our series. Now, what do we do with these? We can't just take this and multiply it by that. That's not how this works. We're going to write out, since we wanted the first 3 non-zero terms of the product, what we're going to do is we're going to write out the first 3 non-zero terms of each one of these, and then FOIL them together. And that will guarantee that we'll get the first 3 non-zero terms of our series here. So let's write out what the first 3 terms of each would be. So I guess I called this one f of x. The first 3 terms of this, if I plug in 0, I get 1. If I plug in 1 into here, I get negative x. If I plug in 2 into here, I get negative 1 squared is positive, so x squared. So this one's coming from the 1 over 1 plus x. And then I do the same thing for e to the negative x here. So that one is going to be 1 minus x. And then the difference here is we have x squared over 2 factorial, or just 2. All right, so what we're really doing is it kind of just amounts to FOILing the first 3 of each series on its own. So when we FOIL these out, let's start by multiplying 1 by all of this. So we have 1 minus x plus x squared. Then we do negative x times that. So we have negative x plus x squared. And normally we would write down a negative x cubed as well, but we don't even need to worry about that because that's not going to be in the first 3 terms. It's the 4th term. So we don't even need to write that down. And then we have x squared over 2 times 1. So it's 1/2 x squared. And then for the same reason as before, I don't need to worry about this x cubed or x to the 4th I'm going to get, because those will be beyond the first 3 terms. So we really only have to FOIL about half of this. All right, and then once we FOILed it, we kind of combine our terms here. Let's combine these. And the result is 1 minus 2x, and then 1 and 1.5 will be 5/2 x squared. And those will be the first 3 terms of our result. All right, so that's how we multiply these series together. All right, let's see. Well, let me answer JT's question real quick. So will the exam have some conceptual questions, or will it be all literally solving differential equations? There will certainly be some if by conceptual questions you need to like maybe like look at a picture or say like what something's going to do in the long run, something other than solving DiffyQs, yeah, there will be a few of those in there. Most of it will be computational, like most of it will be solve the equation or find the Laplace transform or find the first few terms of the series solution. But there will definitely be several questions like maybe look at this like slope field. Remember slope field way back in the first module? There might be something like that in there, or it might be like, oh, is this spring overdamped, underdamped, critically damped? Could be something like that too. So there could be stuff like that, but most of it will be solving differential equations just straight up. Let's see. I think the next one is Joseph's question, lecture 27, homework 9. Okay, let's take a look at that one. All right. 27. That one, and then number 9. Okay, so use power series to solve the initial value problem. This one is kind of this one's kind of silly because when I look at this, I see something as simple as 3x, and I'm like, well, I could just plug that in to the series and see if it works. And 3x actually does work for this series. But in general, if we weren't able to see that, how would we do this? Since they want to know like the entire power series rather than just the first few terms, this is one that we're going to have to look at by looking at recurrence relations. So we're going to have to do that for this equation. But you could also kind of just cheat and see, oh, 3x works. That's going to be it. But let's say we didn't see that. So we have x squared. And I'm going to FOIL this out so I can save a step here. I have x squared minus 1 times y double prime, but I'm just going to FOIL that. So I have x squared y double prime minus y double prime plus xy prime minus y is 0. And this one actually gives me numerical conditions, which is good. It's a lot easier than dealing with a0 and a1. Y of 0 is 0, y prime of 0 is 3. And you can immediately see that 3x satisfies both of those conditions pretty easily. But anyways, let's go ahead and try to do our series solution method. So the formula for y double prime, we have x squared, and then our formula for y double prime is the sum from 2 to infinity of n minus 1 an x to the n minus 2. And then we have minus y double prime on its own, so we just have another copy of this. And minus 1 an x to the n minus 2. And then we have x times y prime. So that one's n equals 1 to infinity of n a sub n x to the n minus 1. That's our y prime. And then we do minus y. So this is the sum from 0 to infinity of an x to the n. And all that stuff needs to end up being 0. Now, there are sort of two things that we need to do with our series solutions here when we're doing it this way. The first thing is we need all of the powers of x to be raised to the nth power. That's our first goal. Then our second goal is to have all of the series start at the same index. So we're gonna first focus on getting all the powers to be just n. Now, thankfully, this x squared helps us out with that goal because we can multiply that in here and bump up our power by 2. So we don't need to make any modifications to this series, at least not yet, because this is already going to be x to the n. On the other hand, this one isn't so lucky. It doesn't have an x squared to bump up its power, so we need to do a re-indexing, it's called. For some reason, they like to change the name of the variable when they do this. You absolutely don't have to do that. The main thing to remember is that if you're going to raise this by a certain amount, you need to lower the starting value by the same amount. So what's going to happen here, let me maybe write this up top. So what do we have? We have n is 2 to infinity and n minus 1 an x to the n. Now what's going to happen with this one right here is this is going to go down by 2 because we want the inside to go up. That's n equals 0 to infinity. And then every n in here is going to go up by 2, not just the power. We have n plus 2 times n plus 1, a sub n plus 2, ran out of room, but there's going to be an x to the n attached to that. So everything, every n has to go up by 2 in there. All right, so we got that part done, and that's good. And then next, we have another lucky circumstance here, because that x will make this b to the nth power. So when we multiply that in, it'll be n equals 1 to infinity of n a sub n x to the n. And then finally, the y term, that already was an x to the n, so we don't need to do anything there. So we really only needed to modify one series for this, so that's good. Okay, so there's our second round of work here. Okay, so now every series is to x to the n, so that's good. That's the way we wanted it. Now we need to get every series to start at the same index. Now, typically what happens is they all have to start at the highest index that appears. So since we have a n equals 2 right there, we would need to pop out terms from each of these three series until we get to n equals 2. So we'd have a bunch of stuff I would call dangling terms out in the front that aren't a part of any of the series anymore, because we need to start at 2. Now, in this case in particular, though, there's something sneaky that we can do to avoid that. So usually when we do the second derivative, like I talked about way in the beginning of this review, we usually started at 2, because if I included, say, n equals 0, that term would just be 0. If I included n equals 1, that term would just be 0 as well. So typically, it's customary to start at 2. But there's nothing wrong with changing it to start at 0. Reason being is that I'm effectively just throwing 0 into the series, which of course doesn't do anything. If I plug in 0 into here, that's 0, so I didn't add anything. And if I plug in n equals 1 into here, the same thing happens. I didn't add anything. So that's a time where we could just freely change that index down to 0. Now you need to make sure that that actually works. If I plug in one of those two numbers, it doesn't make that 0, I can't do it. But in this case, I can. This is already 0, this is already 0. And then we could actually do the same thing for this y prime term as well. If I just change this to include n equals 0, that won't be a problem, because including that term would just be like adding 0. So I could start this one at 0 too. So we got lucky this time. We were able to avoid shooting out a bunch of terms here. Let's see. So now we have everything starting at the same term. We have everything with an x to the n. This is where we combine all the series into one, and then we get our recurrence relation. So we're going to get one jumbo size series here. This is sum from 0 to infinity. N times n minus 1 an, that's our first part, minus n plus 2 times n plus 1 a sub n plus 2. And then we have plus n a sub n, and then minus a sub n. And all of that is to x to the n, and the sum of those things all equals 0. Now, the way that this technically works, this is a series over here, right? Technically, this is actually not an equation of numbers. This is an equation of series. On the left, I have this crazy-looking power series. On the right, I technically have the 0 power series, which is 0 plus 0x plus 0x squared. And two series are only the same when all their coefficients match. So since all the coefficients over here are 0, that means all of these need to be 0 for every single n. That's where the recurrence relation comes from. We could just write this out, and then there's going to be some algebra we can do to make it nicer. I'm actually going to do that a little bit here. Okay, and then I have n a sub n minus 1 a sub n. That's like saying we have n minus 1 a sub n. Remember, all that stuff's got to be 0. Okay, and then notice that there is another n minus 1 a sub n here. Let me get some water real quick. So we can actually combine these guys together. So we could factor out an n minus 1 a sub n, both from here and from here. So when I do that, the leftover term is n. When I pull all that stuff out of here, all I have is just 1. So I have n plus 1 times n minus 1 a sub n minus n plus 2 times n plus 1 a sub n plus 2 is 0. So yeah, so that was just a little algebra trick there. You could also FOIL it out and then recombine it. That's also totally fine to do. And then I'm going to add this stuff over and then divide by those coefficients right there. So when all is said and done, after my algebra, I get an plus 2 is n plus 1 times n minus 1 a sub n over n plus 2 times n plus 1. And this is our recurrence relation. And since we had this in a series that started from 0, this is valid for any n we would care to plug in. So this is valid for n greater than or equal to 0. Remember, these recurrence relations aren't always valid for any n you want to plug in. They start at whatever that starting index was in that last series you wrote down. Okay, now, all right, so let's try to figure out some of these a sub n's and see what our series is going to look like. Y of 0 is 3. No, sorry, y of 0 was 0, so a sub 0 is 0. Y prime of 0 was 3, so a1 has got to be 3. So let's see what a2 has got to be. Well, a2 we can get from plugging in 0 into here. So we're going to get some weird number when we plug 0 into here, but it's going to be some weird number times a0. But what's a0? That's 0. So I don't care what that weird coefficient is. A2 is going to be 0 because it's some product of a0, which was 0. I said 0 a lot. Sorry. Okay. All right. Well, that's fine. Maybe this is going to be one of those alternating series where it only has the odds and then doesn't have any evens. We wanted to figure out a3. Well, in order to get that, we would plug in n equals 1 into here. So if I did that, I'd have a3 is 1 plus 1. Oh, but then we have 1 minus 1, a1, over 3 times 2. Now this time the culprit wasn't a1, that's not 0, but 1 minus 1 is 0. So that means a3 is going to be 0 as well. a4 is going to be something times a2, but that was 0. And at this point, I think we could see that all the even ones will be 0. But another thing is that a5 will be something times a3. But that one was 0, so all the other odd ones are going to be 0 as well. So a4 is 0, a5 is 0, and all the rest of them are 0. So all we have is a1, and remember, that goes next to the x term. So that's a very long-winded reason why y is equal to 3x for this one. Of course, on the exam, if you happen to just see that this works, that 3x will solve the equation, you're welcome to just click it for that reason too. I mean, we're not seeing her work on this or anything. Okay. Oh, let's see. These take a long time, so unfortunately, I don't have any time. Well, actually, it looks like Tyler's question is real quick. Let me take a look at that one. So that has to do with lecture 28. How would we at least start that one? Do I have 28 pulled up? 7, 6, 17, 23. Nope. All right, let's pull up 28. Thought I had that one. All right, let's see. Okay. So question 9. So to be entirely frank with you, the way that they want you to solve this problem is, I don't know, it's not very nice. The way they want you to do it is they want you to use sort of a recurrence relation, but instead of them all equaling 0, they're going to equal some non-zero numbers depending on what sign is. The way I would solve this one is I would kind of use that method I talked about in office hours, and it's also in my other video I just posted today, where we solve for the largest derivative, and then we start plugging in terms to see what our wow, I lost my train of thought. We need to see what our derivatives are going to be, and hence what our a sub n's are going to be. So I guess I could start you off with the first part of this. So with this equation, they start by saying that y prime minus 3xy is 4 sine of x. So the first thing I'm going to do is I'm going to move this 3xy over. And then the x that they want you to center your solution at, they say that that's going to be 0. So it's going to be a Maclaurin series. So if I plug 0 into here, well, first of all, we know that y of 0 is always a0. That's always how this works. And then y prime, if I put 0 in for here, it'll be 0. If I put 0 in for there, it'll be 0. So y prime will just be 0, meaning that a1 is 0. And if we wanted to get a2, we would have y double prime. We do a quick derivative here. I'll speed through that. 3x y prime plus 4 cosine of x. So then when we plug in 0 for this, we won't get 0. We'll get 3a naught, because that's what y of 0 is. This part will be 0, but then we just have a 4 that's not attached to anything. So y double prime will be 3a naught plus 4. So usually with these problems, we have like an a naught and an a1. But in this case, we just have a naught and then numbers that are on their own. Now remember, this is y double prime. In order to get a2, we need to divide this by 2. So a2 is 3/2 a naught plus 2. That's why you see 2x squared in all of these answers, because a2 has this 2 that's on its own. And then we also have 3/2 times the a naught x squared. And then we would just need to do this 2 more times, because it looks like it goes up to x to the 4th. And then we would be all good with this one. All right, we have one final question here. What time is your review tomorrow? It's going to be 11 a.m. So normally I would have that as my office hour on Friday, but Friday is the actual final. So I'm just going to have it 11 a.m. tomorrow. It'll be the similar format. So you guys can just bring in your questions and ask me this stuff, and I'll be happy to help you guys out. All right, that's about it for now. So I will see you guys next time. And of course, if I didn't get to your questions now, feel free to email me, and I'll try to help you out with those. So hope everyone has a good day, and I will see you all tomorrow.